Hello, everybody. So in this video, I'm going to go over the work you guys did yesterday. You guys did some force diagrams. If you have not done the force diagrams for Monday's work, please do yourself. You're not doing yourself a favor by watching this video first, because I'm going to give you the answers. I don't want you to copy these answers onto your homework. There's obviously nothing to stop you from doing that, obviously, but I still want you to save this video I want you to try first on your own. And then come back to watch this video if you haven't done Monday's work yet. So once you've done Monday's work, go and watch this video. So we're going to be looking at force diagrams. Yesterday you guys looked at forces, how to calculate forces. Now we're going to learn how to draw forces. So I'm going to go review some of the tips I put on yesterday's agenda, and then I'm going to just get right into it and show you guys what these force diagrams should look like. I'm going to use as many different colors as I can. Hopefully I might be fiddling with the little drawing tools a little bit, so just bear with me. So I'm going to go ahead and share what I have with you guys. So first we're going to look at yesterday's agenda. Let me make this full screen here. Okay, so here's our agenda. We'll zoom in a tiny bit, so especially if you're using phone, you can see. So here's just some tips for diagramming forces. First of all, you don't have to be a great artist. If there's a squirrel, or if there's like a fancy dresser or whatever, you don't have to do anything fancy. You can just draw boxes. As for a tree, draw a box. As for a person, draw a box. Just draw boxes. So, which I know sounds kind of silly. Why would you do that? But remember, physics, when we talk about physics, we're talking about rules for the universe. And so the forces for rules on a box is the same for rules on a car. The rules for a car is the same for the rules for a planet. The rules don't change based on shape or size, so you can just draw a box for all of these situations. So don't say that you can't, because I know you can do this. We're going to do it together. But number 2 says, before you draw any arrows, it's good to know if the forces are balanced or unbalanced. So here's what I mean by that. And let me get my drawing tools out here. So let's say that this situation says that you have a box. And so if the situation says the box is not moving, then this is a balanced force. When we say that something has balanced forces, because it's not moving. And this is why we say it's balanced. So I got my red box there. Let's say my red box is on a tabletop. So let me use a different color. Oops, I just erased my box. I think they gave me a box option. There we go. So say I have a tabletop that my box is sitting on. And when we draw forces, is one of the tips I'm going to give you down there later to know is that every time that I have an object on the earth, which I think all these situations are on the earth, we always have this force of gravity. So that blue arrow there, that's going to represent gravity. And for that, I'm just going to call that F. I won't let me do subscripts, but F sub G. That's the force of gravity, okay? Now, as I said multiple times on multiple of my daily questions, if gravity is the only force acting on an object, it should be accelerating downward. This box is not moving. We established that already. So if this box is not moving, there must be something to balance that downward force. There must be another force acting upward. Do that a little bit better. Acting upward. And what would we call that force? Well, we would call that force the normal force. So I could just say F N, or I could just say N for normal force. I usually just say N. So whatever you guys want to say. There's my normal force. So it's balanced. So this is a balanced forces because the force of gravity is balanced with the normal force. That downward force is balanced with an upward force. So it's a balanced situation. So it's not moving, not because it's balanced on a seesaw or something. We call it balanced because there are two forces are negating each other, and that's why it's not moving. Now, the first tip actually says if the object is accelerating, then the forces are unbalanced. So let's say that this arrow wasn't here. And actually, I should make this eraser. I should erase that line too. So if this box was only being acted upon by the force of gravity, it would be unbalanced. There's nothing to balance that downward force. And so it is accelerating. Remember, forces cause acceleration. Forces are just pushes or pulls. So this box is being pulled down by gravity. So we call that an unbalanced situation where the net force is 0. So there's nothing to balance that downward force of gravity. That's an unbalanced situation. So this little chart here will kind of tell you if in a situation where the forces are balanced, the net force is equal to 0, and the motion is constant velocity. I'll come back to that. And unbalanced forces, the net force is non-zero, so there's a net force of going down on this box and is accelerating. So net force is non-zero, motion is accelerating. In this case, it is accelerating down. So I'm going to come back to those this chart later on. Let me just keep on chugging here. Okay, scroll down. Try to be consistent by drawing the tail of your arrows from the center of the object and point the arrow in the direction of the force. So I didn't really do that in my last drawing, but try to put your arrows in the center of the object, not to the side, to the bottom, or whatever. It's that just kind of helps things get a little consistent. If I was trying to draw something, if I had a force diagram, let's just take my box again, and let's just take the same situation. I have a box, and then maybe I have it's sitting on some sort of table. If I tried to draw, if I tried to draw the force of gravity is down, and then the normal force is up, and then maybe there's somebody pushing the box, and then I also have friction acting that way. So you can see that it gets a little confusing. You're like, what's going on here? So if I instead draw the arrows where, gravity's going down, start from the center, normal force is going up, somebody's pushing the box this way, and there's also friction acting that way. So now it's a little bit nicer to look at. I can kind of understand what's going on. If you don't know what that diagram is telling you, don't worry. We're going to get some more examples that hopefully you guys already tried from yesterday. And then after that, I just kind of give you some tips of describing what each the forces you guys are going to be using on these diagrams. So all of this is kind of like your little answer bank right here. This is where you're going to see all the forces that are going to be on this practice. I read through the whole practice. There shouldn't be any other forces that are not included here. There are definitely more than just these, 6 forces, but these are the only forces you're going to have the diagram. So I know that part of this assignment is just learning how to recognize what force is what, but we're going to do that together. And by the way, velocity and speed are not forces. So if I have a box, like go right back to my box example. I was like, Mr. Reedy, when are you going to get off this box? If I had a box, and I'm going to draw an arrow, but I'm not going to draw a force arrow. This is just a velocity arrow. If I have some velocity going in this direction, velocity is not a force. So I would not draw a force arrow. If I drew an arrow going this way, well, that would be wrong because forces cause acceleration. Remember that. Force equals mass times acceleration. There is no velocity in your force equation. So this is wrong. We would not indicate velocity by using arrows in a force diagram. So let's go ahead and look at some examples together. And again, I'm going to go through the work you guys did yesterday. So again, if you have not done this work yet, please take some time to do this on your own. I'm going to try to zoom in as much as I can without... Just put my face down there. Okay. No, actually, I'm going to put my face up here because I'm special. I'm important. No, I'm kidding. So, first one says a book is at rest on a tabletop. Huh. This sounds familiar. It's not a box, but it's a book. So, a Freebody diagram for this situation should look like this. Okay, so let me pull out some keywords that I want you guys to tune your brain into. At rest. Whoops. At rest. That's going to be important. On a tabletop. Okay. Those two phrases are important. So let's just draw this out. Before we even think about forces, let's just draw a box on a tabletop. Or sorry, not a box, but a book. Okay. I'm going to make my book green. Why not? And I'll put it on a black table. Okay. Now you don't even have to draw the legs of this table. I'm going to just go ahead and do that just so everybody knows that it's a table. But you don't have to. You can just draw a surface. That's fine. Because we're not concerned about the table. We're trying to think about the book. Okay, so a book is at rest on a tabletop. A Freebody diagram for this situation should look like this. So before I start drawing arrows, I told you it's good to think about, is this a balanced situation or unbalanced? So just think about that for a second. Is this balanced or unbalanced? So unbalanced would mean that the object is accelerating. Balanced means there's no acceleration. So in this case, there's no acceleration because it's at rest. It's not moving at all in this case. So we say that this is balanced. Can I choose a different color for that? We call this a balanced situation. Okay. So now as the diagram is right now, this is we could leave it alone like this if our book was in space, but our book's not in space. So there are definitely some forces acting on this book. Let's think about what forces. Well, so the first force, the really easy force that's going to be on almost every single diagram you do is the force of, hopefully you guys have got it now, gravity. That's a big stinking arrow. Force of gravity. So in every single one of these diagrams, gravity is going to be one of these forces, because I didn't give you an example where the object is somewhere floating in space. Gravity is one of our forces here. Okay, so Fg for the force of gravity. Now, if I left my diagram like this would be unbalanced because this is saying that my object is accelerating downward. So I need an upward arrow to indicate that this is a balanced situation. That's why I said you should identify whether it's balanced or not first, and then you kind of get an idea of how many arrows you need to put in your diagram. So what is balancing the force of gravity? So in this case, is being balanced by the table. The table is keeping the book from moving down. And remember, whenever we said that a solid surface is pushing something back up, we call that the normal force. So I'm going to type it out this time, but I'm going to abbreviate normal in the future, which is a capital N. Normal. Okay, now let's look at our diagram. A book is at rest on the tabletop. There's no left or right motion. It's not accelerating. It's at rest. Force of gravity is being balanced by the normal force upward. Okay, that looks good. And we're done. That's it. Book just has two forces, force of gravity and the normal force, which is going up. So sometimes you have to just think about what forces are they trying to tell you about, and then use the arrows to fit to complete your diagram. So that's why I said a good first step is just to determine, is this balanced or unbalanced? The book is at rest, it's balanced. On a tabletop, the tabletop kind of tells you that there's a normal force present, balancing the force of gravity. And remember, gravity is going to be on every single one of these diagrams. Okay? So let's look at the next one. Number 2, a girl is suspended motionless from a bar, which hangs from the ceiling by 2 ropes. A Freebody diagram for the girl in this situation would look like this. Okay? So I'm not a good artist, especially on the computer. I'm not going to try to take the time to draw a girl. So my girl is going to be just a box. Okay? Okay, there's my box. So she's hanging motionless from a bar, which hangs from the ceiling by 2 ropes. Okay, this sounds really complicated. So she's holding on to a bar. So, I mean, I wouldn't even take the time to draw this bar, but there's her bar. And here's the ceiling. And it says that there's 2 ropes. Okay, whatever. Zoom doesn't really give me many color options here. I'm going to make the ropes orange. Okay. Isn't my diagram very pretty? Yes, it is. Okay, so, before we drew any arrows, let's just look at the sentence. A girl is suspended motionless. So hopefully you guys have keyed into that word motionless. Motionless, which hangs from the ceiling by 2 ropes. Okay, so let's just get this force out of the way. The first easy cheesy force is going to be in every single diagram that we're going to do is, you guessed it, gravity. So here's gravity. F sub g for gravity. Okay. Okay, now if I my force first of all, I'm sorry. Before we do that, I should have said, is this a balanced or unbalanced situation? Well, this girl's motionless. So even though she's not on a surface, she's motionless still. So we call this balanced because she's not moving, she's not accelerating. Okay, so she's balanced. If I left my force diagram like this would be unbalanced. This would mean that she's going downward. She's not going down, she's staying still. So what's balancing her? There's no surface to hold her up. What's holding her up? Well, it's this bar, right? It's this bar with these ropes attached to it. This is where you might have to go back to that little bank on the agenda to see, well, which forces could be holding her up. And if you read far enough, tension is one of the forces that are used whenever you see a word like ropes or chains or strings. So there's 2 ropes in this case. So something called tension runs along the length of these strings, or ropes, excuse me, ropes. You can't really see that color. Use green. I'm gonna use black. I'm trying to find a color you guys can see easily. Black for tension. So tension is balancing gravity. Tension is the force of that works along strings or ropes or chains or whatever. Anything that hangs has this force called tension. And if I use this again, I'll probably T. Okay, so let's look at the sentence again. The girl is suspended motionless from the bar which hangs from the ceiling by 2 ropes. A Freebody diagram for the girl in the situation looks like this. Let's see. Well, this is a balanced situation. We have the force of gravity, like always. Gravity is balanced by tension, which is divided between those 2 ropes. There's nothing. So since it's balanced, it looks like we're done. That's it. This diagram is done too. Just gravity balanced by a single force, just like our first example. Okay. So I'm going to go and clear my drawings so I can go to number 3. Okay, so falling. So falling can be a little bit tricky. Got to read carefully here. So let's read through this. And I'm going to underline some words that hopefully you guys are keen into as you guys read these. An egg is free falling. That's important. From a nest in a tree. Neglect air resistance. Wonder why it says that. Well, let's find out. A Freebody diagram for this situation looks like this. Okay. So first of all, let's think about whether this is balanced or unbalanced. So an egg is free falling. And whenever you see that word free fall always indicates acceleration. This is something that we didn't touch on with our kinematics that we probably could have. But whenever objects fall to the earth, they accelerate. Now there's something called terminal velocity. For example, if you're a skydiver and you jump off of a plane towards the earth, you spend a good amount of time in the air and most of that time you wouldn't spend accelerating because there's a velocity at which you couldn't go any more faster just because of the way the shape of your body is, especially if you have a parachute. If you have a parachute, that terminal velocity comes much quicker. But free fall, for the most part, means that an object is accelerating. Whenever something falls through the earth, it accelerates, which is why whenever you jump off of a tall height, you go faster and faster and faster and faster and faster, which is why it's scary to jump off a skyscraper than it is just like a playground. So free fall means that there is acceleration in this case. So if something is free falling, we should automatically know that this situation is unbalanced because there is acceleration occurring in this case. So this is our first example where there is acceleration. So this one might look a little bit weird compared to the last few ones. Let's make our egg pink. So we have a pink egg, okay? It's free falling from a nest in a tree. So let's just go ahead and get the first force out of the way. It's just a really easy force you should draw in every single diagram. It should be the first force you draw, and that is the force, that is the force of gravity, okay? So here we go, got the force of gravity. I should really, whoa, what happened? Okay, I'm trying to keep my colors consistent. I'm sorry, guys. There we go. Now let's think about what other forces would be acting on this object. Well, whenever an object falls, we know there's air resistance. Oh, wait, it says neglect air resistance. Okay. Well, whenever something is free falling, it means if there's acceleration. In particular, there's acceleration downward. And this sentence doesn't mention anything else. So I think we're done. And actually, we are done. This egg only has one force on it. And to neglect air resistance would mean that there's no air. So this thing is falling through something that has no air, which you don't usually find eggs in a vacuum. So this isn't a very realistic situation. But this example just here to show you that when you're free falling, the force that is causing you to accelerate is gravity, and that's pulling you down. Okay, so we're done. All right, so let's look at the next one. A flying squirrel is gliding. Okay. So let's look at this. I think I might need to move my screen over a little bit. Hang on. Oh. Let me fix this real quick. And this is the point where a professional video maker would cut this part out because they're professional. I'm a professional teacher, not a professional video maker. Okay. Okay, I can't get the line to go away. Whatever. So a flying squirrel is gliding, no wing flaps, from tree to the ground at constant velocity. Here's a really important word here, constant velocity. Consider air resistance. A free body diagram for this situation looks like this. Okie dokie. So let's draw our flying squirrel. Let's do that first. Let's see what this shape looks like. I haven't done this shape yet. Ooh, it's kind of matted. I don't like that. You guys ready to see an awesome squirrel? I should have really got a cut and paste a JPEG of a squirrel at this point. That would have been cool. Well, a squirrel is brown. Oh, I do have a brown one. Here we go. There's my flying squirrel. See, that's my squirrel, in case you're curious. This is my squirrel. Yeah, I'm not going to draw that, guys. Did I spell squirrel right? I think I did. There's my squirrel. Okay, flying squirrel, fly from tree to tree to the ground at constant velocity. Let's just pretend for a second. So this squirrel has some velocity. So maybe he has velocity going in this direction. We know he's going toward the ground. Maybe his velocity more in that direction. Maybe he's going this way. We don't really know. He's going some way. But the important thing, the reason I underline constant velocity is because remember, constant velocity, that's a condition for a balanced situation. So we know that in this situation, our forces are balanced. Okay. So let's look at what forces would be on the squirrel. So the first force that you should draw on every single diagram that you do for this class is gravity. Force of gravity is pulling the squirrel downward. Pulls everything downward. This is the force of gravity. Okay, the same color text here. Okay. Now it says this time to consider air resistance. So, okay, so we know that the squirrel is being pulled down by gravity, but this is a balance situation, which means something has to balance that force of gravity. And if the thing that balances that force of gravity is air resistance. And if you missed it from an earlier lecture, I'll explain what air resistance is real quick. Air resistance is very similar to friction. It always negates motion. It always goes against the direction of motion. So in this example, I'm just going to abbreviate AR. Here, I'll write it out. Air resistance. But it always goes against motion. In this case, the squirrel is falling down, and air resistance is going against that motion of the falling motion. So air resistance is just this force that whenever something is falling, you always have some air trying to catch the squirrel or catch whatever surface that is. That's air resistance. It's pushing up on the squirrel's belly. Okay, so let's think about other forces. A flying squirrel is gliding from tree to the ground at constant velocity. Consider air resistance. Okay, so force of gravity is being balanced by air resistance. We have the air resistance there. This is a balanced situation, so we're done. And some of you are sitting there like, well, he's moving though. If gravity is balanced by air resistance, shouldn't be there another force like somewhere around here to show that he's moving somewhere? No, we don't. Remember, velocity is not a force. We're doing a force diagram. Force equals mass times acceleration. You can have velocity without acceleration. Remember, acceleration means you're changing velocity. This squirrel is not changing velocity. He has velocity, but he's not changing it. So this squirrel is gliding at whatever speed he wants to glide at so he can reach the ground safely. So this diagram is complete because there's no other forces mentioned in this scenario. We don't need to draw anything else. Okay. So I'm going to go to the next one. Excuse me one second. Okay, how many more do I have? We're going to 10. I can hear my daughter start to wake up, so we might not get to all 10. I'll try as hard as I can to get to all 10 though. Okay, so here we get some more unbalanced situations. I already kind of gave away the next one, but that's okay. So a rightward force is applied to a book. I'm going to underline some words as I go. A rightward force, so that's when we know that the force is applied rightward, is applied to a book in order to move it across a desk with a rightward acceleration. So rightward, especially the word acceleration, hopefully you're already keyed in now. If there's acceleration, it's going to be unbalanced. So this is unbalanced. Consider frictional forces. Neglect air resistance. Okay, so we know that friction is going to be one of these arrows, but air resistance is not going to be one of the forces in this diagram. A free body diagram for this situation looks like this. Okay, so I'm going to draw my desk. There's my desk, just going to be a line. I'm going to draw my book. I think we already drew a book. I think I'll do a red book this time. Why not? Here's my book. Okay. So like I said, we already know that this is an unbalanced situation because we have acceleration. And now, so remember the first force you drawn, I need to go blah, blah, blah. Yeah, it's gravity. Okay, I know, we got this. Gravity, sheesh. Mr. Reedy, this video is already like 40 minutes already. So, okay. There, I got gravity. Happy people? Okay, gravity. Now, let's look at, we know there's going to be an unbalanced situation. So if I left it like this, we know this is unbalanced. But let's look at what direction it is unbalanced towards. It is unbalanced to the right. Why do I say that? Well, because it says a rightward acceleration. So up and down, I should be balanced. So when I say unbalanced, in this case, it's unbalanced in the right direction, or in the horizontal area, horizontally. But it is balanced. It's balanced in the, I can't do it. It's balanced vertically. Okay, this is what I mean by that. So it's not accelerating up and down. It's not falling through the desk. So there must be a force balancing that gravitational force going upward. Well, that's the force of the desk. Whenever we have a surface pushing on another surface or an object, we call that the normal force. Where's my line? Where's my arrow? So this, I'm going to use the same color. This is where I already did this in another example. That's my normal force. That's whenever a surface pushes back on an object. Now we have, let's just draw this rightward force. You guys have probably been waiting for this, right? A rightward force is applied. Okay, so I know that there is a rightward force applied. Hey, I want a different color. I want a good color. Okay, so there's my rightward force. So this is just applied force. Whenever I write applied force, I just usually write F. And that's not a cuss word. That's just easy. Makes it easy to write. So there's my applied force, okay? Capital F. Now, it says to consider frictional forces. So if you look back at your little bank of choices for your forces, a frictional force always opposes motion. So I could draw an arrow like this to represent friction. So remember, for friction is the force that is opposing the forward motion. That's the desk opposing the forward motion. But I want to make sure that whoever's looking at this diagram, even if they don't have this explanation, can understand that friction is not balancing this force. This is an acceleration. So since there is definitely a motion to the right, we know that there's definitely motion in this direction. I should make that arrow a little bit smaller to say that, hey, there is friction here, but it's not as big. It's a smaller force. So I'm just going to label that friction. And whenever you do friction, you can always abbreviate with a lowercase f. F for friction. Okay, so now this might be a little confusing, but if you just slowly think about each force, it should be okay. So a rightward force is applied to a book. I got my rightward force to move it across the desk with rightward acceleration. So is there rightward acceleration? Well, if I add this big arrow minus the small arrow, I still have a little bit of force to the right. So yes, that's right. Consider frictional forces. Well, I got the force of friction, which is the force that opposes the forward motion. Neglect air resistance. Well, I don't have air resistance on here. A Freebody diagram, the situation looks like this. Looks good. And I always have to have that gravitational force on here to show that is being balanced by the normal force. Okay. Now the next one is actually very similar. I'm going to read it from the bottom of the screen. I hope you guys can read it too. I don't want to take my time to draw the entire thing, so I'm just going to read this. A rightward force is applied to a book in order to move it across the desk at constant velocity. So this time, I have constant velocity. That's really important. That means it's still going to the right, but it's going at constant velocity. I'm not accelerating anymore. So the situation down here, this is an unbalanced situation because this is balanced because there's constant velocity. So the number 6 is actually the same exact thing as number 5. So if I was going to draw number 6, so I'm going to change this diagram to now to reflect number 6, I would keep everything the same except I'm just going to erase the arrow actually, except for the arrow. The arrow would be going to the left and it would completely balance. So we would say that, whoops. So we would keep the lengths of these two lines equal to show that equal lengths So number 5 and 6 are exactly the same. The only difference is friction is just as big as the applied force because there's now constant velocity. Remember, even though it's moving to the right, I can have motion as long as constant velocity and still be balanced. Okay. All right, we can go to the next one. A college student rests a backpack on his shoulder. The pack is suspended motionless by one strap from one shoulder. A Freebody diagram for the backpack in the situation should look like this. If you go back to number 2, it's the same exact thing. This is the same exact diagram. The only difference is there's one strap instead of 2 ropes. So this might be a little bit confusing because the way that they describe this doesn't really make sense if you think about how people wear backpacks. But in this diagram, you got a backpack. You know, so I'm not taking as much time to explain this one because we've already done something like this. You got a backpack. Let me draw a strap actually. Here's the strap. Okay. So it's suspended from somebody's shoulder. Oh yeah, let me draw a shoulder. Okay. There's a shoulder. It looks like a hand, but whatever. Use your imagination. That's a shoulder. And so the key words here, student rests a backpack. The pack is suspended motionless. So those 2 words should help you realize that this is a balanced situation. And here I have force of gravity. Whoops, excuse me. Draw with the color you can see. The force of gravity being balanced by tension along that strap. Again, something's hanging or being suspended. You should recognize that is tension. T for tension, and then there's gravity. Okay. Okay, next one here. A skydiver is descending with a constant velocity. Consider air resistance. So underline some words here. A driver is descending with a constant velocity. So really, I'm not going to underline this word because we don't really care. I don't really care about which direction he's going in when I draw a force diagram. He's descending with a constant velocity. Consider air resistance. A Freebody diagram for the situation should look like this. So if I didn't have air resistance, I really couldn't do this problem because we know that there's constant velocity. So we know that this should also be balanced. So let me draw my skydiver. It's going to look just like our squirrel because really we've done this already. So I'm going to draw 2 forces here. I'm going to draw a force of gravity. Again, every single diagram. Force of gravity. And then I'm going to draw the upward force of air resistance. We know air resistance goes against motion. The motion would have been otherwise downward. Actually, we do know he's going downward, so I guess that word descending might have been important. Excuse the size of my arrow. Let me try that again. Okay, so there's air resistance. And there we go. So for, air resistance is balancing gravity. Actually, I already talked about this in a previous diagram. Skydiver is falling. He's going to get to constant velocity eventually. That's called terminal velocity. You can look up terminal velocity if you want. So force of gravity is being balanced by air resistance. And we're done. Okay, so let me move on to the last two problems here. If you're still with me, by the way, you're incredibly patient, and I'm glad you're here. I'm glad you want to learn. Number 9, a force is applied to the right to drag a sled across loosely packed snow with rightward acceleration. A free body diagram for this situation looks like this. Okay, so this is snow, right? Let's just kind of set the stage. Let's have some fun. Okay, maybe it's nighttime. And we got some snow. You know what? What the heck? Let's go ahead and draw some stars. Yeah, now we're getting artsy. Okay, I'm going a little overboard now. So we got a sled. Let's draw our sled. Now I can use some lighter colors. Got a sled. It's being forces applied to the right. So, oops. Oh no, what happened? Let's label some words here. Highlight some words. So a force is applied to the right. So this is going to be applied force to drag a sled across loosely packed snow with a rightward acceleration. So that word rightward acceleration tells me that this is unbalanced. Okay. All right. So let's just get that one easy force out of the way so we can just deal with that, the vertical. Ooh, oh my goodness. Okay, so downward force of gravity. So there's gravity. And it's not accelerating downwards, so the snow must be providing a normal force. The snow is pushing back up on the sled in order to keep the sled from falling. There we go, normal force. Okay, so we got the vertical taken care of. Now we know that there is rightward acceleration. So we know that there must be a force going in the right. So maybe there's a guy with a rope on this thing. Maybe this guy is self-propelling with his feet. We're not really told, but we don't have to overcomplicate force diagrams. So we know that this is an applied force. I'll use a different color for that applied force. We know that this is an applied force going to the right. That's all we need to know. Ooh, why can't I use green? There we go. So here's my applied force, F. Applied force F. Okay. Now, if you kept this diagram like this, I might accept it because this meets all the conditions. We have a force applied to the right. We've considered gravity. We've balanced gravity. This is unbalanced in the horizontal direction, which is just what we want because unbalanced means it's accelerating to the right. So this looks good. However, I'm a little bit picky. I would say that there's one more force to consider, and that's friction. So friction would be the force of the snow opposing the forward motion of the sled. Since it didn't tell me to ignore friction, I'm going to go ahead and draw friction. I'm not saying that you have to because snow doesn't really usually have that much friction. So I'm just going to draw a tiny arrow saying that, hey, there's a little bit of friction here because if I kept the sled on the snow, it will eventually stop. It might not stop right away, but it'll stop. So a little F for friction. There we go. So it's still accelerating to the right because my force to the right is much bigger than my frictional force to the left. There we go. Okay, now number 10 is probably by far the hardest, which is, so I'm kind of glad that we were able to make it to number 10. You can thank my sweet daughter for sleeping this long. Yay. So I'm gonna make a little more effort to draw this car so we can understand what's going on. Oh, a car with square tires. That's great. Oh, yeah. Oh, yeah. Look at our car. It's coasting. You don't know what coasting is. It might be good at this point to look it up. Coasting means that your foot is off the gas. You're moving, but your foot's off the gas. Coasting to the right. And slowing down. A Freebody diagram should fit the situation looks like this. So before we draw anything, let's just think about, is this balanced or unbalanced? Is there acceleration? Remember, acceleration means a change in velocity. If something is slowing down, it is changing velocity. So this is unbalanced. My nice pink color there. Unbalanced. Because it's changing velocity, okay? So let's just keep that in mind as we draw this diagram. And actually, let me draw a road for our poor car here. Our poor boxy car. Probably gets terrible gas mileage. Okay, so there's our road. No, I don't like that road. Here's our road. Okay, so again, first force you should always draw blah, 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 blah. Gravity. Force of gravity. Okay, there's force of gravity. Make that the same color. And we know that this is slowing down. We know that the force of gravity is not pulling it down because the road is there. So it'd be silly to say that the car is being pulled down by gravity because it is being pulled down by gravity, but gravity is not causing it to fall through the road. So there's still the upward force of the road, which we call the normal force. Okay. Now it's slowing down. Now you might be tempted to say that is coasting to the right. So there should be an arrow to indicate that forward motion, right? And this is a lot of people make the same mistake, but let me just tell you that this is not right, okay? So if it's coasting to the right, remember velocity is not a force. It's coasting to the right, but it is not moving forward. It's slowing down. So we have to think about which direction is this accelerating. So if you have something that's moving forward, but it's slowing down, that means that there has to be a force that's pulling it in this direction. So again, it's moving forward and slowing down. Something is pulling it from this direction to get this car to stop. And this happens in real life too. No car can keep moving forward unless you have the gas on. Even if you have the gas on for a while, you're accelerating and then you stop accelerating, you're going to be decelerating because of what? There's a frictional force that is pulling you backward. So there's a frictional force between your tires and the road, or maybe the axle and the body of your car. I'm trying to find a good color to use here. That frictional force is what is slowing you down. So even though it looks a little funny to have only 3 arrows on here, this would be the complete drawing. So there's our complete drawing there. We got the force of gravity pulling the car down, normal force counteracting gravity because the car is not accelerating up and down. So remember, the acceleration is backwards. So slowing down means it's losing velocity. So even though it's moving to the right, we have to show that it's being slowed down to the left by the leftward force. There is no force on the right because this car is not accelerating rightward, it's accelerating left. Whenever we say something so we call negative acceleration is the same as slowing down. Deceleration is the same as slowing down. So the car is decelerating by that leftward force there. So this is a hard one. It's probably one of the hardest ones just to get visually, because this diagram makes it look like it's moving to the left. But remember, forces do not make velocity. Forces make acceleration. So this car is accelerating backwards or to the left because of that frictional force. There's no force that is making this car go forward at this point. Okay, so you guys are going to get some similar problems to do today for force diagrams. I just wanted you guys to get some practice with these. These are hard concepts to get. I just wanted you guys to get some practice. If you have any questions, please come see my Zoom tutoring. I don't see that many physical system students in my Zoom tutoring class. If you guys are watching this and we're no longer in the COVID quarantine, good for you. Thank you for watching this video. And you can ask me any questions in class. You can get a hold of me by email or text, or you can just comment on this Google Classroom assignment, and I will see you guys later.